Well, good morning. It is April 1st, and I'm not fooling about that. April Fool's Day. It's just, it really is April 1st. Oh, you guys are still asleep. All right. So today I want to go over these 4 problems that we worked yesterday, and then I want to go over 2015 kind of together. It's kind of a unique one where it talks about an air cell, which is a unique type, but we really do everything the same way. Then we're just going to kind of continue on. Everything so far has been at standard conditions. How do we calculate E cell if it's not at standard conditions? And we're going to learn about what we call the Nernst equation. It's just kind of plugging in, and it kind of relates. We're going to be talking about Q again in that, but it's easier than the previous Q problems. It's more plug and chug. So when we're looking at this, okay, so we have our cells here. A student is given a standard galvanic cell represented above, that is copper electrode and tin electrode. As current flows through the cell, the student determines that the copper electrode is increasing in mass and the tin electrode decreases in mass. What does that tell you? When it says that this one is increasing, copper's increasing in mass, tin is decreasing in mass, what's that telling us? Because we have Cu2 plus in here and we have Sn2 plus in here. That's a lousy 2. Copper's being reduced, okay, because what's happening? It's gaining the electrons and it's being precipitated onto the copper electrode, correct? Whereas what's happening to the tin? It's dissolving, it's coming back, it's losing the electrons and going into solution. So its mass is decreasing. So that's a way of telling you which one, rather than giving you the reduction potentials, and the more positive ones being reduced, the less positive ones being oxidized, we also need to know about mass increasing and decreasing. Okay? So, identify the electrode in which oxidation is taking place. Okay? And which one is that? Tin. And we call that the anode or the cathode? Anode. Equals oxidation. Okay? So the electrode at which oxidation occurring is the tin electrode. Explain your reasoning based on the student's observations. So what would be the explanation?
Since it's being reduced, some of it has to dissolve back into solution.
Since it's being oxidized, some of it, what? Keep going.
Has to dissolve back into solution.
Is dissolving back into the solution, thus the mass of the electrode decreases. Okay? Y'all, when I read some of y'all's test free response questions, you try to, you're too skimpy. Okay? We don't want to be verbose. We don't want to have too much wording, but you need to make sure you're answering it fully and completely. Okay? So just don't say, it's because one must be dissolving, or just don't give one little phrase or something. Explain, as the tin is oxidized, it goes into solution, causing the mass of the tin electrode to decrease. Okay? Now, where does the mass go? And someone just said it, what? Into the solution. The electrons are flowing, but the electrons aren't really contributing much to the mass. The tin is just going from here, the solution's getting heavier, this electrode's getting lighter. Total mass always remains the same because matter is neither created nor destroyed. It's a simple, it's such a simple question that it's almost tricky. Then in the expanded view, which is down here, but we'll just use this salt bridge up here, okay? It's KNO3. So let's just talk about which way are electrons flowing? From what? Which electrode to which electrode? Say that again, Anna. From the tin to the copper. Electrons always flow from anode to cathode. Electrons originate in the anode, they end up terminate at the cathode. So the electrons are going to be going this way. Okay, and all the way around. So what's happening in the salt bridge then? You got K plus and NO3 minus. Which way is the K plus going? K plus is going this way, right? NO3 minus is going that way. Always the negative always just continues in the same direction. Positive is going to go in the opposite. Because again, if you want to look at it just from a practical, the copper is coming out of solution, so this side is losing positive, so the K plus replaces it, keeping everything neutral. The amidst solvent molecules, use arrows showing the movement of particles. Okay, what's the function of the salt bridge?
To maintain neutrality.
Okay, it closes the circuit, but what?
Maintains electrical neutrality.
Okay, it allows ions to flow to maintain electrical neutrality. That's the phrase you need to, and they will ask that question about a salt bridge. Notice in this packet, 14, 15, 16, 17, 18, there's an electrochemistry question every year. Okay? Almost every single one of the questions involves a salt bridge question. The function of the salt bridge is to allow ions to move to maintain electrical neutrality in each cell, if you want to be more specific. It allows ions to flow to maintain electrical neutrality in each cell. Okay? Hey, very doable question. Okay? Nothing really super difficult, no high level math. Okay, we just need to understand the basics of that. That was, you wanted me to repeat, is that what?
Yeah, that's fine.
Is everybody good as far as understanding and being able to draw this and understanding how to do electrons? Now, it's not asking for this, but how, because, again, I didn't get the video ever to work. How would I calculate E cell for this?
Right.
Say that?
No.
E cell is equal to E red minus E ox. Okay? Now, for problems like in the textbook, that's going to be, we're going to get it from page 1106. There's going to be, you can find all these values. On the AP test, if they want you to find this, they're going to give you the values in a chart somewhere in the problem. Okay? Now, what does this degree symbol mean?
Standard.
Standard conditions, which are what? Temperature is 25 degrees Celsius, pressure is,
Atmosphere.
and concentration is 1 mole. Okay? So E cell, now we're gonna determine that at the end of today when we talk about non-standard conditions. We're gonna differentiate between the two. So someone look up. So if I'm looking at this, they're all in reduction potentials. So it's going to be Cu2 plus 2 electrons goes to Cu solid, and it's going to be 10 2 plus 2 electrons goes to, not Cu, Sn solid. So somebody look up for me on page 1106 what those values are.
10 is negative
136
and copper
is 0.34. one's just used so much, I remember that one. Okay? So, and again, what did we say is being oxidized? Which one's being reduced?
It's being oxidized.
10's being oxidized, therefore it's going to be 0.34 minus the negative 0.136. So my E cell is going to equal 0.1476, 0.476 volts. Did it ask for that earlier in this? It didn't, right? Now, what would be the balanced equation for this reaction then? What plus what?
SN plus CU2 plus.
SN solid plus Cu2 plus goes to
SN2 plus Cu,
now Reagan, how did you know to start with 10 and not SN2 plus?
Because I just thought how that solid is losing mass, so it's reacting, solid reacting.
Because the oxidation reaction is this reaction. This is the oxidation reaction for 10. So everything on the chart is written as reduction potentials, but one of them is going to be oxidized. So it's going to go the opposite direction. So whatever one is being oxidized, that part of that half reaction is going the other way. Okay? So I'm going to start, this is being reduced, so copper is gaining the electrons, but tin is being oxidized, so it's losing the electrons. So the copper reaction is going this way, but the tin reaction is going that way. Now again, remember that the oxidation potential is always just the opposite sign. Some books say E cell is equal to E red plus E ox. But when you plug in the value for E ox, you change the sign of what's in the book. This negative sign does the exact same thing. I just think it's easier just to say red minus ox and not have to worry about changing signs. Okay? Does everybody understand that mathematically? Okay? You either add it and change the sign with this number. Okay, so what we would do here is add it but change that sign. We end up getting the exact same thing. All right. So those are just a couple of things as far as doing here. And again, remember, look at this one. When we did this, okay, we had these two equations here, the copper and the chromium, and we put them together. And the chromium is, this is negative, so the chromium is the thing being oxidized, so it's coming, we wrote it this way, chromium going to Cr3 plus. But to balance this equation, why did we have to put those coefficients in there? Because it's 1 to 1, 1 to 1.
they're balance the electrons.
You have to balance electrons. You got to balance charge as well. So since it's a 2 and a 3, we know that we have to put a 3 and a 2. So now it's plus 6 and plus 6. We balance the charge. Okay, so if you have a simple equation like this, and I think, was this the first AP problem I think we looked at? I don't know. And then we do one yesterday at the very end of class. I thought we did. Maybe not. Okay. What we did? We did like 1980 something, 1993 or. Great time to ask questions if there's anything here that we don't understand. All right. 2016. Now 2016, I gave you all of the starting information on this one, but we really don't need that to be able to do this. Okay, that's the torn page that I gave to you to add in on this problem. Okay? Now D really is not an electrochemistry problem, but it's a good review problem. Explain why I2 is a solid at room temperature, whereas Br2 is a liquid. First off, what determines whether our substance is a solid, liquid, or gas at room temperature? In this case, the IMS, because they're both covalent substances, right? It's the strength of the bonds holding the things together. In an ionic bond, it's that lattice energy, the strength of the ionic bond. In a metallic bond, it's the strength of that bond between the metal atoms. In a covalent network, it's the covalent bond between the carbon atoms in the diamond or the graphite. So those are all very strong, so those are all solids at room temperature. Okay? But then when you get into covalent molecular, what are our three types of intermolecular forces? LDFs, hydrogen bonds, dipole-dipole. Okay? What type of substance are both of these? They're diatomic, so are they polar or nonpolar? So what's the only type of attractive force between the two? LDFs. And with what do LDFs' strength vary? The size. Technically the size of what? Electron cloud, not the mass. And AP is real picky about that. Okay, so the electron cloud is larger, therefore more polarizable. So since iodine's electron cloud is larger than bromine's, we know that by periodic trends, just looking at iodine's, bigger. Okay, it's got more electrons. So what does that mean about its LDS? Stronger, allowing it to be a solid, where this is can be a liquid. But it's still, iodine's a solid, but it still is one of the substances that sublimes readily. What does that mean, sublimes? Changed this directly to a gas. So even though it's a solid, it has stronger LDFs, they're still weak, and it can still just very easily be broken apart and go into the gas.
So what do they like to use for the electron cloud stuff? Is it like more polarizable?
More polarizable, because the bigger the cloud is, the more smushable it is. More, and your book actually used a term, I can't remember, it wasn't smushable, but it was something very similar to that, as far as polarizable. It can be distorted more readily, more completely, which is going to make the more electrons that get on one side, the more distinct the negative side is and the positive on the other side. All right, so that has nothing to do with here. So while cleaning up after the experiment, the student wishes to dispose of the unused iodine in a responsible manner. The student decides to convert solid I2 to I- ion. So is this going to be the oxidation or reduction to go from there to there? It's being reduced, right? So what does that mean in terms of the voltage here? Does it need to be the more positive or the less positive voltage? It needs to be more positive, okay? So here's the reduction potential for I2 going to I-. All right? So which one is going to be less positive than this one? The top one. Okay? So this one is the one that would get oxidized. So if it's getting oxidized, which way is the reaction going to go? It's going to go this way, right? So when it says, which solution should the student add to I2 to reduce to I-, okay? First off, we know we want to pick this reaction because it's the one that's less positive. As far as which one then of these two, S406 or S203, remember we're going to start in oxidation, we're going to start here and go this way. So we want to use the S203 to mix with the I2. That's your sodium thiosulfate. That was one of the ingredients in our kinetics lab. I think it was ingredient C. That was our thiosulfate that was waiting. That was waiting for the iodine. As the iodine got produced, it reacted with the S203 and took it back to I-. Okay, so the purple color didn't appear until there was no more S203 in our kinetics lab. We did this exact reaction. I know that you guys are remembering that clearly and concisely. Okay, but we did do this. This was the second, the reaction. We had the first one where we had, it was S2O8 was reacting with Ki, the I minus, and it was making I2, but as soon as the I2 got made, it reacted with the S2O3 and went back to I minus. And then we had starch in there, and when starch and iodine are together, it makes that bluish purple color. But as long as the iodine got used up quickly, it never had a chance to bind. But as soon as the S2O3 ran out, the iodine built up, it turned blue. We stopped the clock. Oh yeah. Okay, just remember there were two reactions going on there. A slow one, the first one was slow, and the second one was fast. The fast one was this one. Okay, just trying to show you that, you know, relating what we did to these problems, that it really is all kind of the same thing. So write the balanced net ionic equation for the reaction between iodine and the solution that you picked. So what's that equation going to be? S2O3 2 minus plus I2. So again, this one is being reduced, so we're going to start and go left to right with this one. This one's being oxidized, so we're going to go right to left with it. Goes to 2I minus plus S4O6.
It's 2S2O3 on the left side.
It's 2S2O3 on the left side. Okay, so now we have 4 and 4, 6 and 6, 2 and 2. What about charge?
It's 4 minus 1.
Okay, so what do we need to do?
Nothing.
Okay, so we're balanced, right? Because minus 4, minus 4. Okay? That's all for that problem, right? D, E, and F?
Justify part E with a calculation.
Oh, E for the calculation. So what is E cell going to be then? 0.54 minus 0.08 is equal to 0.46. Now, why would we think that that one would be spontaneous or thermodynamically favorable?
Because it's positive, and when it goes into like the G equation.
Okay, because a positive E, that's all you really need to be able to say. When E cell is positive, that means that the reaction is thermodynamically favorable.
So for the 0.08, why did you make it negative? If it's going to
E red minus E ox. So this is E ox, E red minus E ox. On the other ones, I have the negative. I put a parenthesis negative, which really means minus. A minus, I change it to a plus. And again, that's because oxidation half reaction is opposite sign. So the oxidation potential is negative 0.08. So you can either say E red plus E ox and put in a negative 0.08, or just say E red minus E ox and put in the positive, and then this negative changes. Either way. But it's always just E red minus E ox, red ox. And it's a redox reaction, so red ox. We all good with that? Okay. When we go through these other two, then we're going to come back and we're going to look at the stoichiometry part of A, B, and C of this one. Okay, just to review some stoichiometry on how to do that. And then I also want to go over 15 with you. Okay, for those of you that were not here, what was it? Today is Thursday, so it was Tuesday afternoon, the second period. Are you guys starting to see how to calculate E cell? That's kind of what we went over in that. I mean, I'm trying to fill in the gaps because I didn't have that on video. So we're trying to, I'm being a little bit over-explanatory here for y'all. I'm trying to fill in those gaps. But, so you're feeling like you having an idea now what's going on? Okay. Ask questions, y'all. Ask questions. 2017.
Yeah, I read,
Okay. A student wants to determine the concentration of H2O2. Now, H2O2, does anybody recognize what common compound that is? Hydrogen peroxide, the stuff you put on your cuts and scrapes. Okay, H2O2, it's just nice to know that's a real common compound, just be able to recognize it. But because it's a peroxide, what does that make the charge on each oxygen? -1 instead of -2. Okay, so that's why it's kind of good to recognize that that's hydrogen peroxide. That means it's an O2 with a -2 charge, or each oxygen's -1. And then when it goes to normal water, it goes to the -2. Okay? So, all right. So, a student wants to determine the concentration of H2O2 in a solution of H2O2. The student can use one of two titrants, either dichromate or cobalt-2. The balanced chemical equations for the two titrations are given below. Okay? So here are my equations for what's happening. So they're telling you now in the equation which one's being oxidized, which one's being reduced. In each case, notice the cobalt is being oxidized. The chromium here is +6, and it's going to +3, so it's being reduced. Okay? So we have to kind of look at what's going on here. So, how do we do this?
You have to subtract 1.33 from 2. Wait, never mind, I don't remember.
How do we do this one? What are we looking for? Okay? We know that the H2O2 needs to get converted into H2O, right?
Oh, so for the bottom one, you have to multiply by 3 to make it 3H2O2, right? You would think
What are you comparing it with?
the top thing.
Okay? First off, what's happening with the peroxide? In the discussion part, what are we changing to the peroxide? Okay? It's in a solution of water, okay? The titration is this. In this case, it's going to be chromium is here. The H2O is being oxidized. So this reaction is which two equations? The bottom two. Okay? Chromium plus H2O2. So the H2O2 is being oxidized in this one. What's happening here? Which two equations? Top two, right? But this time it's this one's being reduced, this one's being oxidized. So how do we know which one to pick? So what? What about the E cell? The positive one. Okay? I think one of them is going to come out negative, I do believe. Okay? So, this one here, E cell, is equal to E red minus E ox. Okay? So in this one, which one's being, we just said the cobalt's being oxidized, right? So this is oxidized, this is reduced. So it's going to be E red, 1.77 minus 1.84. That's going to equal a negative something, 0.07.
So for the top one, do not multiply by 2.
You don't have to worry about doing any of that because we're not adding those equations together as far as, you know, now if we want a balanced equation, well, they actually tell us that these are your balanced titrations for each one. But we're not adding these two together. We're just, it's this and this one, but they've already multiplied this one by 2. Because it's 1 electron, 2 electrons. So they multiplied by 2 already to balance that equation. I think that's what your question was. So what's the E cell for this one? Which one's being reduced, which one's being oxidized here? This is being reduced. This one's going to be oxidized in the first equation. Okay? Are y'all following me? So what's my E cell on this one going to be?
1.33
Which is equal to a positive 0.63. So the positive one is the one that's going to actually occur. If you mixed and did this one, this reaction is not going to happen. It's thermodynamically unfavorable. So the two are just going to mix and not react really.
How do you know the first equation's awesome?
Because I'm looking here at this, I was looking here because cobalt's going from +2 to +3. Because remember, the way we recognize a redox is a change in oxidation states. As the oxidation state goes up, it's oxidation. That's where the term reduction comes in, is when the charge is reduced, it's gaining electrons. And then here too, the peroxide in this one at -1 here, but, pardon me, on this one. It's -1 here, and it's going to 0 there. So now the peroxide is being oxidized in that one. Okay, so you look at, I guess the nutshell answer is you look at the change in oxidation states. Okay? I like it, you guys are asking questions. Okay, I've done all that, I haven't even looked at what the question is. Okay, let's start answering the question. Use the information, calculate E for the reduction and calculate E for the reaction, so that's what we just did. Okay, what's the next part to ask?
Which should they choose?
Which one should you choose? Obviously, we were going to choose this one. Why? The positive E cell causes it to be a thermodynamically favorable reaction. This one's really small. Now, 7, here's 2, calculate delta G for the reaction. We haven't talked about that, but this is a good time to talk about that. Equation that's on your equation sheet. You don't have to memorize, but you're going to be given. The relationship between delta G, it's equal to negative NFE, where E is your E cell. N equals moles of electrons transferred. So is all this on the camera? F is equal to a Faraday, named after Michael Faraday, who did a lot of work on this, and it's equal to 96,485 coulombs per mole of electrons. Now, if you remember from way back, really in Chemistry 1, we talked about a Millikan's oil drop experiment, where he watched the drop of oil between two lines, but he was able to determine the actual charge on an electron. The charge on one electron is measured in coulombs. Well, you take that charge and multiply it by Avogadro's number, 6.02 times 10 to the 23rd, and you get how many coulombs, what's the total charge on 1 mole of electrons. And that turns out to be this many coulombs. Sometimes the 3 sig figs just say 96,500. But this is the number that's given, this is the constant, and it's given on your equation sheet as well. Okay? So that, this number is always, this is always that. So it's a constant. N is the number of moles of electrons transferred, and E is your E cell. Now, when we talk about moles transferred, when we look at this, how many moles of electrons are transferred here? What's N going to equal in this one? Total number of electrons transferred.
1 or 2.
Well, it's 2 to 3, so it's 1 per cobalt, but we have 2 cobalts, so it's a total of 2, right? Here, the same thing. You have 2 oxygens going, each one's going -1 to 0. Actually, here you have 6 oxygens, right? So we have to look at how many electrons, and this is going, this one here too, is you want to look, chromium's going from +12 to +6. You can either pick the oxidation or the reduction because they have to equal each other. So how many electrons are being transferred here? 6. Okay, so N would be 6 on this one. N's going to equal 2 on this one. They just want delta G for the reaction we picked, right? Okay? So, and we picked this one. So N's going to equal 6. So delta G is going to equal -6 times 96,485 times my E cell of 0.63. And that comes out in kilojoules per mole. And what does that come out to? I mean, it's just really plugging it. The hardest part of this is figuring out N. But in your balanced equation, it's the N is after you cross multiply and make electrons gained equals electrons lost. That number that you're canceling out on both sides, that's N. Y'all following me on that? Remember when we're balancing the half reactions? We make electrons gained equal electrons lost. It's N is that final total number after you multiply in the balanced equation. What did we get on this? Then again? -360. Now notice, for a spontaneous reaction, we know delta G has to be negative. Which means in order for delta G to be negative, E has to be positive. So the 3 things that we've seen here, and we're going to relate it to K here in a second, but for spontaneous reactions, delta G has to be negative, less than 0. K, for it to be a spontaneous product-favored reaction, K is a greater or less than 0? Greater than 1, right? Okay, and so it's going to be, if it's a decimal, then it's going to be reactant favored if it's greater than 1. So K has to be greater than 1. And now E just has to be greater than 0. E has to be positive. Put a big star by that in your notes, that's important. Just know that relationship. We have one more equation to relate. We related G to K. Remember we had delta G equals -RT natural log of K. We have delta G is equal to -NFE. So now we just need to have one equation that relates E and K, which is coming up. Woohoo! Good stuff. You guys are just really learning real chemistry just so you know. This isn't baby chemistry. This is real deal. We're at the back of the book. Come a long ways, baby, as they say. There's an old cigarette commercial for Virginia Slims. It was a cigarette designed for women. It's now women's equality. The commercial was, you've come a long ways, baby. Now you can smoke with freedom. Now you're able to kill yourself if you want to with cigarettes. All right. Well, we probably don't have time. A student sets up a galvanic cell, and by the way, galvanic cell, voltaic cell, and a Daniel cell, all three kind of the same thing, okay? Voltaic and galvanic are probably the more common. I think it was Daniel Galvani was the guy's name that came up with this. 298, so that's standard temperature. 1 molar, so we got standard conditions going on here. Student measures the voltage of the cell shown above and discovers that it's 0. Identify the missing component of the cell.
The salt bridge.
The salt bridge is missing. Okay? They're all going to have these salt bridge questions. Okay? So, and explain the importance for obtaining a non-zero voltage. What does the salt bridge do? Allows ions to flow to maintain electrical neutrality. See, because what happens is, as soon as some of, whichever one, let's just say, haven't done it yet, whichever one, if silver's coming in here and chromium's going out here, the charge is going to build up just like that on each one, and it's going to stop the flow before it really even starts. Okay, so we need a salt bridge. The student adds the missing component to the cell and measures E cell to be 1.54. As the cell operates, Ag plus ions are reduced. Use this information in the table above to calculate E for the half reaction of chromium plus 3 electrons. Okay, how do we do that?
It's an equation.
What equation?
0.8 minus x equals 1.54.
This is B, because we know E cell is equal to what?
1.5.
No, well, just what's the general equation?
E red minus E dot.
E red minus E ox. So rather than having you calculate E cell here, they gave you E cell, right? What's E cell? 1.54. I forgot today's Thursday. I was waiting for the bell to ring at 9:05. I've only been teaching at this school for 20 years, and I still struggle with the schedule. 1.54 is equal, so it says that the silvers are being reduced, right? So that means it's going to be 0.8 minus E ox. Right? Now the math right there should be pretty simple. E ox, bring that over here, 1.54, so E ox is equal to, what does it want? It wants the reduction or oxidation potential. Okay, but it's going to give me, what we have here is, this is going to be the reduction potential, because we put the minus sign here. So what we get here, so it's going to equal negative 0.64. 74, good math, Steve. I am older now. Senior moments are becoming more and more prevalent. Okay, so that's your, it's really not your E ox, it's really your E red. Okay, that's where this form of the equation is going to hopefully not mess you up, because I don't want you to change the sign back to positive, because this already changed the sign. Write the balanced net ionic equation then. What do we get? Somebody tell me, what do we get? Somebody on the back row. If silver's being reduced, what do we start with?
Silver.
Silver,
Solid. The solid. Wait, no. I don't know.
80 plus.
so this one's being reduced, right? That means this one's being oxidized.
Alright.
So what do we start with?
Renee, is that?
Ag plus,
And the salt.
plus, which one?
CR solid.
Cr solid, that's right. Goes to Cr3 plus aqueous plus Ag solid. Now is that balanced? What do we need? Three what? Three Ags, because we have to balance the charge. So the first thing is, again, reduction goes left to right, oxidation's right to left. Then we have to balance the charge. Yes, sir.
So, we didn't have to do the thing like where you add H pluses and.
No, not on something like this, no. That's what I'm saying. The only time you're gonna have to do that is a multiple choice.
Okay,
These are the type of things they give you in free response,
okay.
where you really just have to look at charge. That's why the shortcut method, if you can just kind of look and, you know, kind of figure out how many electrons gained, lost by each one, and then cross multiply, it goes a lot faster, in my opinion.
Okay.
But whenever you do these E cells, it's always half reactions, which is why I want you to be familiar with half reactions as well. And then I think this is delta G again, right?
Yeah.
So what's N gonna equal in this one? 3, right? Because it's going from 0 to plus 3. Or it's going from 3 plus to 0. So delta G is going to equal negative 3 times 96,485 times my E cell, which we got to be E cell. Okay? This is the kind of mistake I would make, is I would use the 0.74. But that's not the E cell. What's the E cell? 1.54. Very easy math if you just know what you're doing. If you've never seen this before, then I don't have clues what to do. But now it should be easy money. These problems should be easy money problems. Hopefully next year we actually are going to do just kind of like the English language is doing, is get $100 if you make a 3 or better. I mean, I make money if you guys make a 3 or better. That's the most important thing. But I haven't heard anything, so I don't know if we got accepted or not. I don't know if they're still just looking, whatever. I submitted it a couple of stuff before Christmas.
Is that speaking money or just a blank check?
Blank check.
Alright, so do you get extra if you make a 5?
Nope.
Alright, 2. Well, take 3.
You guys get extra if you make a 5 because you get college credit, and you don't have, that saves you thousands and thousands of dollars.
It's a great pool.
If you get a 5 on the AP test, you get 8 hours of credit at Alabama. And it's usually somewhere around $500 to $800 a credit hour.
Yeah, but if you want, if you're taking chemistry, let's say, go into the medical field, you probably end up taking.
Well, you'll take, you don't necessarily have to, it depends. Some medical schools do, some don't, but I mean, if you go and start in organic chemistry, you're gonna be, you know, fine.
Like from this class to
Yeah,
organic?
yeah.
I mean, yeah.
If you make a 5, then you can probably do that. If you make a 4, you probably might wanna take, if you make a 4 and you take chemistry at Alabama, you're gonna cruise through it with an A easy. If you make a 3, you're gonna wanna, a 3 or lower, you're gonna wanna retake it. It'll still be easy, but it'll fill in gaps. Your brain, as much as you are gonna maybe hate to have this realization, your brain is gonna take all that you've been learning, and in your subconscious, you're gonna be organizing it and dealing with it to where when you go, and you're maturing, your brain doesn't really fully mature until you age about 25, okay? And that's why some of your critical thinking skills are just now, puberty and all the hormones from puberty actually kickstart the frontal lobe of your brain to where all the critical thinking and higher order thinking skills actually occur, which is why you can't teach calculus to a second grader. Their brain just isn't ready to handle it yet. And so you guys are just kind of learning how to use all of that and learning technically how to think. And as you go to college, all of a sudden, you take the exact same stuff in chemistry. Oh, it makes so much more sense to me now. And partly it's just because your brain has had a little bit more time to mature and really learn how to, you know, it's not that you're not smart, it's just your brain is just, you're just starting to work it out in that part of your brain. It's just a growing up thing. Then you get to my age and everything starts going in reverse. It's really kind of sad. It beats dying. But, okay. Are we good with all this? Any questions? Confident? This is going to be a good grade test? Comprehension survey. We don't do tests in here. We do surveys. Okay? All right, let's let me quit talking for a bit. And I want you to go back to 2016 to the sheet that I tore out and gave to you. And look at the stoichiometry part of that problem. And let's just take 10 minutes or so and see if you can work out the stoichiometry part of that problem.
Is that A, B, and C?
That's A, B, and C.
Exciting.
Oh. The part you have all X'd out.
Yeah.
In the 2016, there should be an A, B, and C right there. Right. No. Did you print yours offline? Yours? No, I gave it to you. No, the packets were defective, and so I don't see any more of the envelopes that we have.
Wait,
There's an extra one.
There is?
what?
Oh, that's the one.
Yeah,
I
this
need.
has
Open what?
All you gotta do
Oh,
is
it's
tear
not?
that one page out and add it to yours. Everything else is repeat. In that packet.
I'll think about it. Okay, see if it fits someone else. No.
And you know that live in Greystone Farms, your internet just keeps going out. Sorry.
This minus this. Everything else.
Are you giving up or you have an answer?
I'm giving up.
Okay, I hear a lot of kind of talk and whatever. I think some of y'all are overthinking this, making it a little bit more challenging. Okay? First off, for part A, given that metal M is in excess, calculate the number of moles of iodine that reacted. Well, if M is the excess, what does that mean I2 is? The limiting reactant. So how much of that is left at the end?
None.
None. So all that you added in got used. Okay? So that's what this is telling me, that since M is excess, I know that all the I2, well, how much I2 did we add?
1.02.
Okay? So grams of I2 are going to equal what minus what?
127.570 minus that one.
Okay? So it's going to be 127.570 grams minus 126.549 grams. So that's going to equal how many?
1.021.
1.021 grams of I2. But they want moles.
So divided by the molar mass.
So it's going to be times 1 mole over,
126.9.
that's I2.
Oh yeah. Dang it.
253.8.
0.004.
Let's go with 4 sig figs.
4.022.
Okay? These zeros are not significant. Pay attention to sig figs still on a math problem like this. Okay, so that's A. Now B says, what's the molar mass then of M? Well, first off, what does molar mass equal? Grams per mole, right? So if I'm going to get the molar mass of M, I need the grams of M and I need the moles of M. Well, from our balanced equation that's given at the top there, what's the relationship between moles of iodine used and moles of M used? 1 to 1, right? So how many moles of M are there? 0.004023 moles of M, because moles of M. So now we need grams used. How do we get that? All I heard was a mumble.
Subtract the first two.
Subtract the first two, but that's going to be the total amount used.
Subtract the 1.2, the 1.248 minus the 1.021.
Okay? So here's your 1.284 grams is the mass of Mi2. What are you going to subtract?
The mass of the iodine.
The mass of the iodine, which is the 1.021, because that's how much M is in the final compound. Right? So the mass of M is equal to the mass of Mi2 formed minus the mass of iodine. Does that make sense? Because we know how many grams is 1.284 grams is the final mass of the product. So we know that all the iodine got used, the 1.021, so the rest of it has to be M. So that's going to equal 1.284 minus the 1.021 And that equals
0.263.
0.263. So then my molar mass is going to be 0.263 grams divided by the 0.004, 65.4, 64.5, 65.4 grams of M. Then you could go to the periodic table and find an atomic mass, and you'd find that the zinc has an exact atomic mass of 65.4. So metal M is probably zinc. Okay? So we just got to kind of think through logically on some of that. Now, you may have gotten lost on part B. But A, most of y'all I think pretty much understood how to get to A. B, okay, yeah, I don't really know how to do that, but C is completely, the student thinks it's ionic. How could we test Mi2 to see if it's ionic or not? Well, what do we say? What are different things? What are the properties of an ionic
You
substance?
dissolve it in water and see if it conducts electricity.
Dissolve it in water, see if it conducts electricity. That's the easiest way. It'd be an electrolyte. Two other harder ways that are given in the, the great scoring guidelines. You could melt it and see if the molten form conducts electricity. Or you could just try to melt it and see, does it have a super high melting point? Because if it has a super high melting point, it's probably ionic. Because covalent compounds, it's not one of our covalent network substances, because nothing iodine is covalent network. It's not going to be metallic because it's not a pure one thing. So it's either ionic or covalent. Covalent substances have very low melting points. Ionic substances have very high melting points. So you could have just used the melting point. The easiest would be dissolve it in water. Does it conduct electricity? So, probably 2 points. Let me see if I keep it up. I'm just saying we're on a point scavenger hunt, so you can get points for A. Part A is worth 1 point. Part B was worth 2 points. And then part C was worth 2 points. Okay? So if you just could explain that, you can get 4, you can get 3 out of the 5 possible points. Okay? And then the rest of it, you pretty much should be able to do the electrochemistry part. So if you can get, again, you need to get 7 to 8 out of 10 points on each one to make you 5. You don't have to get them all right. You don't have to know everything. You just got to know 3/4 of everything to get a 5. Yeah, you know 60% to get a 4. All right. One more. Let's look at 15. Early forms of metal air cells use zinc as the anode. Okay, so what does that mean is happening to the zinc? It's being oxidized. Zinc oxide is produced as the cell operates according to the overall equation below. Using data in the table above, do we not have that?
It's on the other page.
It's on the other side. Okay? Calculate cell potential for the zinc air cell. So what do we do for that one? How do you find E cell for that? How do you do A1? Nobody? Really? Do we not say E red minus E ox?
Oh, yeah.
No. E cell, E red minus E ox. They tell you which one's being, they give you the equation. So go ahead and do it. We have all of this in here, but we're using, they give you sodium oxide and calcium oxide. Do we need to worry about any of those? So what do I use? What minus what?
0.34 minus -0.35.
Where are all those extra sheets at? Okay, so what am I going to put?
0.34.
This is what I'm given. I'm going to say, this is the one being reduced. We just said zinc was the anode being oxidized, so it's going this way. The oxygen's the one being reduced, so it's going to be 0.34 minus negative 1.31.
I thought, why wouldn't zinc be going from +2 to 0?
It's going from 0 because we're starting with zinc plus O2. Zinc solid plus O2 is going to ZNO, whereas ZNO is the +2 state. The balanced equation that they tell you in the problem.
Okay. So you have to look at that to decide.
Well, they tell you that that's the reaction that's going on, it's a zinc plus O2 goes to ZNO. Zinc is out, zinc is the anode. So you're told that. So that turns out to equal 1.65. So it says here, early forms of the melt layer, so use zinc as the anode. Zinc oxide is produced, so we're going from zinc 0 to zinc 2 plus. Oxygen's going from 0 to -2, or 2 minus. The electrolyte paste, OH minus, contains OH minus. On the diagram on the cell above, draw an arrow to indicate the direction of migration of the OH minus. Which way is the OH minus going to want to go?
To the right. To the oxygen.
Okay? What's happening to the zinc here? And it's forming Zn2 plus O, right? What's happening over here on this side? What's the oxygen going to? Just think of it like this. Okay, here's your anode. Electrons are always flowing from the anode to the cathode. Okay? So the NO3 minus, okay? So electrons are flowing this way. Okay, actually, this was confusing me. It's going this way. The nitrates are just going to continue. The negative is going to continue in the same direction. Okay? So in my E cell, which way are the electrons? This is your anode. The electrons are flowing this way. Right? And it's telling you that. So which way is the OH minus have to go? OH minus has to go that way. Just follow the negative. The negative is just going to keep the loop going. Does that make sense? Are you with me? You guys are starting to fade. It's been a long day already. Luckily I had you first. You'll be tired the rest of the day. All right, so there, where am I? Right there. So, a fresh zinc air cell is weighed on an analytical balance before being placed in a hearing aid for use. As the cell operates, does the mass of the cell increase, decrease, or remain the same? Ben, you're shaking your head.
I know it's either increase or decrease, but I don't know which one.
Decrease.
Increase.
You're just guessing?
Think,
Think about it.
isn't it being oxidized?
It gets oxygen from the air, so what does
It's there. Say that again, Reagan.
the oxygen comes from the air.
This comes from air. It's a zinc. It's a metal air cell. But again, we had never talked about those. That's why I wanted to do this one together and just kind of point out some things. But the oxygen's coming from the air. So what's happening to the mass? Increasing, because it's not, you're not considering the air. You're really only measuring the mass of the zinc to start with. So the mass is going to increase. Justify your answer in terms of the equation for the overall. In other words, oxygen's coming from the air, therefore oxygen's being added as the reaction proceeds, the mass increases. Okay? We were theoretically supposed to get to this today, but we haven't. We'll come back to this one. Okay, what happens when it's at non-standard conditions? When you go higher altitudes, you don't have as much oxygen, you don't have 1 atmosphere of pressure anymore. And so it's going to change your cell potential. We have to talk about that. That'll be first thing tomorrow. Metal air cells need to be lightweight for many applications. In order to transfer more electrons with a smaller mass, sodium and calcium are investigated as potential anodes. A 1 gram anode of which of these metals would transfer more electrons, assuming that the anode is totally consumed during the lifetime of a cell? Justify your answer. Okay? So we have 1 gram of sodium and we have 1 gram of calcium. We want to know which one's going to deliver more moles of electrons.
Probably
Well, what is sodium going to go to?
the Na2O.
Well, but it's going to go to just Na plus, right? Whereas calcium, okay, plus 1 electron. Calcium is going to go to Ca2 plus 2 electrons. So for every mole of calcium, 2 moles of electrons are going to be transferred. For every mole of sodium, only 1 mole of electrons is going to be transferred. But they don't have the same molar mass, so what do we need to do? Since this is per mole here, what does this need to be? Moles. So 1 gram of sodium times 1 mole over 22.98 grams times 1 mole of electrons for every 1 mole of Na. Somebody get me a number for that, please.
0.0
0.0435 moles of electrons. So that's how many moles of electrons 1 gram of sodium has to offer as it goes through. But calcium, 1 gram of calcium times 1 mole, 40.1, look right up there, what is it, Amar, number 20, 40.08,
7,
40.07.
8. No, 8, yeah.
But this one is 2 moles of electrons for every 1 mole of Ca. Now you can see that we're multiplying by 2, but 40 isn't quite double this. So this number is going to come out to be a bigger number, but what is this number? 0.0499 moles of electrons. Okay? So calcium is going to deliver, it's going to last longer, it's going to be a better battery than sodium is. You know, for lightweight, 1 gram is going to produce more. That's kind of what a chemical engineer, somebody trying to design a hearing aid, you're going to be looking at. Well, how can I make it the lightest, have enough voltage to make this thing happen, and kind of go through all those processes. All right. Good day. Just finished everything just in time. Hopefully we'll be finished by midweek of next week with all information necessary.